So, welcome back from break. Hopefully, it was restful and you're ready to get going. This is computer networking. So, the textbook, oh, let me see. There we go. Power is a good thing. Project One, Intro to Wireshark, has been posted, and it's to get you comfortable with a so called packet sniffer. I will take 5 minutes of today and actually bring it up and kind of drive you around Wireshark. It's available for free. If you Google search Wireshark, it's available for free and it runs on all the platforms Linux, Windows, and Mac OS. If you are on Mac OS and Linux, you'll need to make sure that the network interface has permissions for you to browse. And I'll talk a little bit about that in a moment or two. So that is due in a week. Please make sure you download that. You look at the assignment and you download Wireshark, install it. It's a relatively straightforward project assignment intended to get you familiar with basic use of Wireshark. Okay, and so the textbook is going to be computer networking, a top-down approach, specifically the seventh edition. Of course, between the fall semester and spring semester, there's only 3 weeks, so I'm not sure the bookstore doesn't have it. Probably not. Not confident about that. But this book is available pretty cheaply, much more cheaply than in the bookstore from a lot of sources. Amazon. It's available used as well as new, and also in electronic form. So just get a copy of the book. If you do not have access to the seventh edition, you'll at least need access to the questions in seventh edition, specifically for the written homework. There is a difference in the network layer. It's been separated into the data plane and control plane. So effectively, there are differences between the sixth edition and the seventh edition, particularly in our conversation about software-defined networks. So there will be some substantive differences. So it behooves you to get the seventh edition. Okay, so class meeting, you're all here, so you all know. Office hours are Wednesday, subject to change. Usually what happens, it takes about a week or so into the semester for me to nail down my schedule. Running a project in the maker space, as well as have graduate student advisees and have some research grant proposals and other stuff going on. So certainly subject to change. I intend to have a YouTube playlist for computer networking and data analytics, but for computer networking for this class. So that you can go back and re-listen to things that have been said. It is not a substitute for class. You are expected to attend class to have questions answered, and there are things that happen in class that won't end up in the editing from the YouTube playlist. So that is linked, the URL, through Blackboard. It's your responsibility to check Blackboard regularly, and also created a Slack channel. You can freely join it, and the Slack channel will be the primary mechanism I'll use to communicate with you about questions outside of office hours, about questions about homework and things like that. If there are questions of a personal nature, if it's a personal issue or maybe something related to your academic performance, there is a thing called the Federal Educational Rights to Privacy Act, or FERPA, and I take it seriously. And so if you ask me a question about your tests, quizzes, any sort of academic information, please contact me privately. Don't post it publicly on the Slack channel. You can do that with a point-to-point message on Slack or via email if you choose. And if you ask me for academic information like grades or averages or what have you, I use the grade book on Blackboard, but if you have other specific questions, please use your official DSU email address. I will not answer to anything but the official DSU email address for FERPA reasons. Okay, any questions so far? All right, so with those administrative bits, assessment. We have 5 projects, and I try really hard to try to distribute the components of the assessments as close to uniformly as possible as I can, because I recognize the fact that different students have different strengths and weaknesses. Maybe you have test anxiety, or you do much better on projects. So nonetheless, we have 5 projects with 25%. 4 homeworks worth 20%, 2 written exams worth together 25%, and then there's a research project. The research project is your final exam. A lot of students in the past have used their research project from computer networking to get a job, and I have a couple examples of that in the subsequent slides. And also class participation. I expect this to be interactive. It's how you learn from one another, as well as a good way of getting to know the material a little bit better through discussion. There will be extra credit for this class specifically for your participation in cybersecurity competitions. And so throughout the year, there are online competitions and there are in-person competitions. And if you just furnish proof of your participation in those competitions, I will validate it and award you 5% extra credit. And the reason for that, and I'll get to your question in just a second, is that it's really important to participate in these sort of things. And also, the material that you learn in this class is directly applicable and useful in cybersecurity competitions. Kristen. Yes, yes, anything related to computer networking, cybersecurity. A couple years ago, I think 2 or 3 years, no, 3 years ago, or was it 4 years ago now, when I taught this class, some students in the class participated in Cyber Aces and they placed first. It was like a capture the flag type competition, and it was network security focus. And so, in particular, and thank you for asking the question, any kind of cybersecurity or network related competition like ACES, be it online or in person. Okay. All right. Any other questions? Does that make sense? Okay. So please make sure, and I said this in my other class, it's not fun, no one, faculty member, neither myself or any other of my colleagues in the division, we do not take pleasure when a student does not do well. And the primary reasons I found for a student not doing well is not doing the work, right? Not passing in the work, not engaging the material. And so, for example, one homework is worth 5% of the grade. If you don't pass in a homework, now the maximum grade you can get is 95%. If you don't pass in 3 homeworks, the maximum grade you can get is 85%, which is a B. So do not deprive yourself of the conditions for success by not showing up, i.e. not doing the homework. Okay, and please make sure you follow instructions. That's another reason why students don't do as well as they want to sometimes in my classes, is by not following the instructions. Get so excited about doing one thing, maybe there's a lab exercise with Wireshark, and then you're asked a couple questions, follow-up questions based on the experimentation, and you forget to answer the questions, right? So please make sure you read, you think, and you follow instructions. Because I want you to be successful. We have lots of examples of students who've used the material from this class specifically to obtain great internships and great employment. Okay, so read the syllabus, the schedule. This particular class has a lot of moving parts. There are a lot of pieces that collectively comprise the computer network. And so to make it a little bit easier, I have a comprehensive schedule for all of the topics, all of the sections in the book, as well as the dates when things are out or due. Sometimes I slip that schedule. Some things might come earlier, some things might come later. And I also include points in the schedule for overflow, meaning that if I'm a little bit behind, I can catch up with that empty period. Each year, I try to incorporate something that's current in industry or in the research labs in a class. And this year, I haven't decided yet for this class what it's going to be. I would love to talk about 5G as part of this class. For maybe 3 lectures towards the end of the semester, but it's all predicated on my ability to get suitable material for it, because a lot of them aren't really sharing the underlying mechanisms and how it works for 5G. 5G is going to be rolled out in a major way this year. Okay, you've probably seen announcements from T-Mobile and Verizon. Okay, all right, any questions so far about the assessment? So just do a little bit every day. There are a lot of moving pieces, and so it's going to be really important for you to keep up with the reading, right? The focus of this class is for you to understand different choices you can make for various components that collectively comprise a computer network. And then when you make certain choices, what behaviors or capabilities that gives rise to, right? So that's what we're going to learn. Office hours. I won't belabor this. I have posted office hours. I welcome you there. It gets really lonely in office hours. No one ever visits. But they're there for you. You don't have to schedule an appointment for office hours. But anything outside of office hours, I ask that you schedule an appointment so it allows me to best prepare to help you the best way that I can. And so my preferred mode is electronic, whether it's by email or Slack, so we can arrange a mutually agreeable time outside of office hours if it doesn't work for you, right, for your schedule, because I understand everyone has different schedules. So if I'm in my office, please don't assume that just because I'm in my office outside of office hours that I'm necessarily available at that moment. I have a lot of other obligations and I'm always working on something. And if I'm working on something else, I'm not prepared to really help you the best way I can. So please help me to help you by arranging appointments outside of office hours if you have a need for that. I'm often online at night. So I answer people via Slack, and I've done things via Zoom video and all sorts of things. I try as much as possible to make it easy to provide help if you are need some questions answered and things like that. So please make sure you schedule outside of office hours, but for the posted office hours, you don't need an appointment. Okay? Just all right. So to be successful, so it's going to be really important to read regularly. The book has been accused of being wordy, right? They have lots of great examples. It's the #1 computer networking textbook in the world at this moment, and it has been for the last few years. But that wordiness means there's a high page count. And so it's really going to be important for you to spend that 30 minutes to an hour every day to read the book. It's an easy read. It's also entertaining in certain ways, but it's a recipe for failure if you wait until you have something due to all of a sudden do the reading, right? So that 8 or so pages a day is about the right rhythm for keeping up with the material. And actually, it's a lot more stress-free, if you will, if you engage the material every day. Do that with all your classes. Okay, so I encourage you to discuss concepts with your classmates, right? With your colleagues in the class. It's a really important way to learn the material, both for the person who is receiving the instruction from a peer, as well as for the person who's given the instruction. You have to understand the material in a much more sophisticated way in order to explain a concept with someone else. So I encourage you to do that, but that does not mean you share answers with one another, right? If you're not practicing coming up with solutions, how do you expect to be successful with the material? Okay, so basically work hard every day, right? It's a marathon, do a little bit here and there. The book is wordy and there are a lot of moving parts, so it's going to be really important to make sure you keep up with the reading. Okay, any questions? Okay, so cheating. Do your own work. I don't need at this juncture to talk about academic dishonesty. If it looks like a duck, guess what? It's a duck, right? So I understand that sometimes things happen. People get stressed out. Don't cut corners. I ask you to communicate. Things will happen in general, that's life, but just communicate. Do not give someone an answer. It's painfully obvious to me whether it's an answer copied from off the internet, and I know there are hundreds of such sources, Course Hero, Coursical, all the other stuff. So please do your own work. You'll understand the material, and it'll really show through come job application time, internship time, senior capstone, and stuff like that. Every year I catch instances of it. Make sure that you are doing your own work. I do encourage you to collaborate, but there's a fine line between collaboration and academic dishonesty. Talk about algorithms, talk about concepts. Don't give someone your code, don't give someone your project, don't give someone the answer. Right? You can discuss what the material means, discuss concepts and things like that. But where you cross that line is where you're giving away solutions to somebody or copying it from someplace that you didn't produce yourself. Okay? All right. Any questions about this? And if you ever have a question is this cheating or not? Please, again, I ask you to communicate. If you don't feel comfortable communicating with me, talk to Dr. Rasamni or any other faculty member in the department. Okay? All right. Any questions? All right. So what is this course? Now, my goal this semester, which is 17 weeks long on the calendar, 16 weeks in terms of the actual class time, because we subtract spring break, is to educate you for a career, not just a vocation. And so we will cover rigorously, and I stress rigorously, major and important topics in computer networking. And the goal is for you to develop mastery of the engineering and scientific principles. And what I mean by that is kind of, you can think of it as like the physics of computer networking. There are a lot of choices that you can make for all of the components that collectively facilitate the passage of data from one endpoint to the next. And the choices you make will affect that communications. And so what I'd like for you to walk away with at the end of the semester is a deep understanding of what those choices are and what that gives rise to when you have certain choices for the various components working together in concert to enable communications. Okay, so that's my goal for the semester. You'll gain experience in concepts employed by applications that use networks. And so you might have a career where you never touch a computer network per se. Maybe you write applications. And more applications are distributed applications, and therefore having an understanding of the underlying network will help inform better choices as to what you do in your applications. Okay, so we'll also talk a little bit about concepts and applications that use networks. You'll also gain, and this is an important part, experience in the assessment, experimental design, triage, diagnosis, and understanding of these trade-offs. And so computer networking, a top-down approach, takes the approach of understanding networking by its instrumentation. And so we'll make heavy use of a network packet sniffer called Wireshark. It's freely available, and it's very much used in industry for you to be able to visualize and measure and run experiments and make decisions or answer questions based on measurements on campus for the network, or you can do it off campus as well. Okay. To understand the physics of computer network is the goal, right? So what is this course not? You're not going to learn how to configure Cisco networks. Now, Cisco is the predominant network component vendor in worldwide, I would say, I dare say. And this course is not about building computer networks with Cisco products. Now, of course, after this course, you'll understand how to configure a Cisco network component. You'll understand issues when you connect routers and things like that together, but this is not about Cisco networking. So if you've had some Cisco stuff previously, that'll be helpful, but that's not what we're going to do. We're not going to assemble and build computer networks. You're not going to learn the largely defunct 7-layer ISO model, right? That's largely defunct in the modern internet stack. So that's not what our focus is going to be. You're not going to learn application frameworks. So we're not going to learn, JSON RPC, right? Doing JavaScript object notation to do RPC calls. That's not what this course is about. Okay. All right. Any questions? No. All right, so course alumni, right? These are just a sampling of some of the things students have gone on to in the last 7 years who have taken this course, and I list them because it's opportunities that they've obtained directly as a result of their computer networking final project. What did they do? They just talked about what they did for their project. So there's a lot of employment, a lot of opportunity out there if you're really good and have mastery of computer networking concepts, especially in the wireless space. I'm going to try to put some wireless stuff this semester because it's unavoidable given the onset of 5G rollout in 2020. Okay? All right. So Wireshark. First, any questions? No questions? Yes. As of tonight, yes. Yes. So you don't have to have it downloaded at this point, but you're going to need it for this first assignment. Yes. Okay. Any other questions? All right. So Wireshark is a so-called packet analyzer, and sort of in more casual parlance, a packet analyzer is also called a packet sniffer. And so you have your host, your computer, which is this icon on the left, your left, and then you have a switch or router, if you want to call it. And later on in the semester, you're going to learn that this isn't the router, right? This device that you call a router that you might buy in Best Buy for $100. It's performing a bunch of things that we'll talk about. So you have your computer, you attach it to the network, and it's running the 5-layer internet stack. And so physical, transport, physical link layer, network transport, and application layer. The bottom four are running in your operating system, and we'll spend the whole semester talking about the details of what these are. But the important part here is that we have some application, and the application wants to reach out over the network and send data, produce data, or consume data. Now, of course, when you do this, you're going to get units of data called packets. And those packets have certain fields in them, and those fields can take on certain values. And based on what those values, the endpoints and the various pieces of equipment in between the endpoints are going to respond based on what that content is in those respective fields in your packet, which is the unit of data. And so inside of the operating system, you have your packet capture driver. And this packet capture driver talks to the network card, also called the network interface. And it takes this raw unit of data. And what this packet analyzer does, it's an application called Wireshark, and it understands all of the different fields of the packet and what the different values those fields can take on, and will write a human readable form of them. And so that's a so-called packet analyzer. And what it does, it takes a copy of every single packet that's going on to the network. And that's whether it's your packet, so-called point-to-point mode, or if it's any other packet that someone else is putting on that same network, so-called promiscuous mode. So this packet capture, PCAP, is a driver. It's a low-level piece of software within the operating system that knows how to interact with your network interface card, and it renders or draws out all the information associated with all the packets that go swirling by on the network. So I'm connected to CIS Wi-Fi, right? And so anyone who's on CIS Wi-Fi, it's wireless. And so each of your laptops is sending out wirelessly, connecting with CIS Wi-Fi's routers. So because we're all on the same network, we can physically reach one another's machines broadcasting. So that means anything that you send across the network, my packet analyzer, my Wireshark installation, will see those things, right? So if you're not scared yet, after doing this assignment, it should scare the hell out of you, right? Just how vulnerable network communication is, which is why encryption and safe security practices are really, really important, right? So let's take a look at Wireshark. So I'm going to pop out of here. First, any questions about the high-level view of Wireshark? No? Okay. So hopefully I'll do this right. So let me exit and show. Okay. So I downloaded Wireshark from wireshark.org or something like that. It's not a .com, right? If it's a .com, you're at the wrong place, and someone might ask you to pay for it. Wireshark is absolutely free. It's available on all the major platforms: Linux, Windows, and Mac OS. So I've already downloaded it on my Mac OS installation, and so I'm going to run it, and it looks like a shark fin. And so what will happen when you first start up, it'll give you a listing of all of the different communicating interfaces that you have on your machine. And so I'm going to select the wireless communication interface, Wi-Fi, which is also labeled with a name, right? And so that name is the so-called interface, and on Mac OS, it'll give EN and some number for all of the interfaces there. Now, typically, most laptops have two interfaces, one for the wireless communication, the wireless network card, and one for the wired network card. So you'll minimally see in most modern machines, most modern laptops, you'll see two interfaces. So I'm going to go ahead and I'm going to double click on my wireless. And you'll notice, without doing anything, you see a lot of information going whooshing by. And let me just stop this just so that I don't fill up my hard drive. And so here you'll see in the top part, you'll see a number of windows. And in this top window, you'll see a summary. And the summary is numbered, bless you, on the first column. Now, this first column is the number of packets that are received, this unit of data. Now, it starts at 1, and it keeps incrementing and going and going and going. Just for this brief amount of time, maybe 10 seconds, you'll see that I've collected over 12,000 packets, right? So this will fill up your hard drive if you let it run for a really long time. And so this data window is a depiction, a summary of all of the packets that are captured in the order in which they're received. Now, of course, I'm not physically really doing anything on my machine, but there's a lot of stuff going on. I'm running Dropbox. So periodically, Dropbox is sending and receiving across the network, polling for files. My system is always trying to discover things like what printers are available on the network. It's also doing other maintenance type things as it pertains to addressing and leases for keeping an IP address. And we'll talk about all of that stuff over the course of the semester. So what you'll see in this summary interface in the top window here, you have a bunch of columns, and we have which packet it's received, the time in which at which it's received, right? So you can talk about the so-called inter-arrival time between packets. It'll have the source IP address, and we'll talk about what IP addresses mean, but it's a number uniquely representing a network card. So for example, this packet, it's the 12,186th packet that my machine has captured. The source IP address is here, the destination where that packet should be going, and then the protocol, right? And we'll talk ad nauseum this semester about the protocol. Protocol is nothing more than a particular format and a particular set of actions that are taken when you get certain fields in a packet of information. And then it talks about the packet length, how much data it has, and there's a summary about information. So let's try something out, and that's where I'll ask for your participation. And what we'll do is if somebody brings up their browser, right, um, and just go to a website. It doesn't matter what the website is, right? So I'm going to first run Wireshark. Who's going to be a volunteer? Who wants a volunteer? Yeah. Okay. Well, I have a bunch of people. All right. So I have a bunch of people. Hopefully, it's not too much data. All right. So I'm gonna run Wireshark, and then when I say go, enter in a URL and type enter. Okay. So all right, go. Let me know when you're done. Are you done? Done? Okay. So I'm going to give it another few seconds, and then I'm going to stop. So now your browser uses something called HTTP, Hypertext Transfer Protocol, which we're going to talk about in great detail. But for now, one of the things you can do, there's a little field here at the top of that topmost half window in Wireshark, and you can type in a protocol name. Right, so you'll see here a protocol says TCP. In the browser, the protocol is called HTTP for Hypertext Transport Protocol, and that HTTP is a so-called application layer protocol because the application, i.e., your web browser, is what interacts or understands what that HTTP protocol is. It's a conversation between your web browser and the web server. Question. Oh, okay. Oh, I see. TLS is transport layer security, and we'll talk about that too. This is there's so many, so that's why I say make sure you keep up with the reading, right? Because there are tons of moving parts, but it all fits together as we go along. And so that's a security transport protocol, right? And so we'll talk about all of that. I just can't talk about it in detail now. So let me type in HTTP. HTTP. Let me type it in all caps. Cancel. HTTP. I hear Tansy in my ear. It's next door. Because in my microphone. I don't have HTTP. Let's see. Hmm. Let me check and make sure. Capture options. It's in promiscuous mode. Manage interfaces. Save. All right. So why don't we cancel? Why don't we try that again? All right. I'm going to start the capture. Continue without saving. Why am I not capturing now? All right. If you could hit the web page, reload, please. All set? Okay. So let me stop. Um, HTTP. What was your website? Reddit and YouTube. YouTube might not work because it does dash streaming. All right, so let me boy. All right, let me do it myself. I wonder if it's not doing promiscuous for HTTP. All right, let me try this. Bring up my browser. Yeah, that's true. Let's see. Cancel. HTTP. HTTPS. Let me try lowercase. No, it should still be HTTP. The S is just encrypted. All right, so let me just try. Anyone know their IP address? No? Okay. Darn it. All right, so what I'll do is I'll run it and I'll just show you my own. All right. Continue without saving. So let me pick a website. Let me go to I don't know. Let me go to IBM.com. All right, so we go to IBM.com. It might be the organization of our network. So let me try HTTP. HTTP. There we go. So there's HTTP session. And anyways, all right. So here's an HTTP connection. And the source IP is 10.33.21.195. That should be my IP address. Let me check if config dash dash A. EN0 is 10.33.21.195. Yeah, so that's my IP address. It's not allowing me to do promiscuous mode on this network. All right, so nonetheless, the source IP is my machine. The destination, that should be IBM's. And you'll notice if I go down to the section, the box down below, I can expand each one of the layers in the network layer stack. The top layer, which is displayed on bottom, to be completely confusing, is the application layer, and you'll see it says Hypertext Transfer Protocol. It's a GET message, and here's the URL. It's been hashed for security's sake, and it's running HTTP 1.1 request. And so I have a certification host, and it has some other information that we'll talk a little bit about, just very ancillary. And so this Wireshark allows you to view all the network traffic. And not only does it view the packet information, it teases out all of the bits of information at each layer in the protocol stack. So TCP sits right below HTTP, or HTTP is built on top of TCP. TCP stands for Transmission Control Protocol, and that's the mechanism in place in the transport layer for what's called reliable data transport. And so this also has certain information, right? And so you can look at the network layer, protocol information, um, the link layer, which is what gets you onto the network. So that's my wireless network card to communicate in wireless broadcast radius. And then it also has the physical information, the framing. And so all of this is to say, this packet sniffer allows you to capture packets and to view the contents of those packets. So you could imagine then, let's say you're in an airport, you're in a public facility like an airport or coffee shop or what have you. So let's say, you're in an airport in New York City or what have you, and people are, trading stocks, or they're looking at stuff related to their stocks, right? If they're not secure, i.e., encrypting their communication, you can absolutely intercept what the people around you in network radius are sending and receiving. And not only is there value in information if you see the actual data, but also the pattern of communication. So, when you go to www.google.com, instead of just going to HTTP www.google.com, it goes to HTTPS www.google.com. And so the reason for that, the S means that it's secure, it's using secure sockets, and essentially before sending that data over the network, it's encrypting it so that somebody intercepting it with something like Wireshark can't make out what you're doing. Because if you were doing a Google search, if that Google search is not encrypted, people can actually see the search terms that you're looking for, right? So you can imagine if someone is searching for private information, or maybe they're searching for stuff related to a medical issue or what have you, without this encrypted version of the Google web search, HTTPS, you'd actually see the search terms, because those search terms are appended as a suffix on the URL, right? Which is why in this case of the IBM.com, for the HTTP, you'll notice this is just gobbledygook, right? That's because it's encrypted. And if it weren't encrypted, I would actually see what it is that that resource was that I was trying to get off of IBM.com. Does that make sense? And so your assignment is to use Wireshark, install Wireshark first, and to use Wireshark, run through a Wireshark assignment experiment, and then to run a couple experiments on campus and see what you find. Now, of course, over the summer, the network was upgraded through our partnership with Apple. And so I'm not completely sure what you're going to see or if you're going to see things, but you should see something. And so there are some questions at the end, in addition to the assignment, that I ask you to answer after running a series of experiments. Okay? All right. Any questions about this? And so you should be in promiscuous mode. I'm not sure if this network is not allowing me to see packets that are not to or from my machine, but certainly other parts of the campus might not be blocking that. Okay? All right. Any questions? No questions? No, make sense? All right. So with that, let's go back to uh, the slides, excuse me, and continue on. Okay, so let's get started. Ready, steady, go. All right. So the purpose of the first chapter is to really establish the terminology and the services and the components that collectively comprise a computer network. And the whole goal is for you to learn the vocabulary and learn some of the high-level issues before it jumps into all of the individual layers. That's the application layer first, the transport layer second, network layer third, and the link layer last. And so in doing so, we will look at all the components and their relationship with the adjacent layer and issues concerned with various choices you can make at each one of those layers in the 5-layer stack. And so we'll talk about what the internet is. We'll talk about protocols at a high level, the various components, both the edge devices as well as the devices in the interior. We'll talk about the structure of data in the core as well as the components, and we'll look at delay. We'll just consider it a high level security since you can take a whole class on network security. And so my purpose is not to show you exhaustively what security issues are. And we'll also look at protocol layers, and we're not going to cover internet history. It's in the book if you're interested, but I'm not going to, in the interest of time, hold you responsible for it. Okay, so what is the internet? In the nuts and bolts view in the book, they talk about all the components. And then they also introduce what's called the service view to look at all of the behaviors and capabilities that each one of these components have. And so this is a general depiction, excuse me, of a network. And so you have a network here called an institutional network, and this is something like what you'd have here at DSU. It's a large enterprise, so we have the dormitories, we have the academic buildings, we have the classroom buildings, we have rec centers and campus centers and stuff like that. And so each one of those components, each one of those buildings or entities has a network. So you have a bunch of entities that are interconnected with one another, and they can communicate. Now they all connect to these devices called routers and switches, and these things are responsible for storing and forwarding units of data or chunks of data that are standardized sized called packets. Now here you have an institutional network, and this institutional network, like DSU's, is connected in through an internet service provider or ISP. And that ISP has what's called a switching fabric, right, which is a set of routers, high-speed routers, that are interconnected to one another. And there are so-called regional ISPs that might serve like maybe the greater Philadelphia area, greater Baltimore area, the whole mid-Atlantic, and so forth. And those regional ISPs excuse me, connect into global ISPs. And those global ISPs might serve entire countries or continents. And so these global ISPs will connect into other things, these regional ISPs as well. One might be your home network. And this is products like your Xfinity through, was it Comcast, and your Fios product through Verizon. And I know RCN has broadband and some other providers that I'm not familiar with. And so your home network is your typical setup where you have this device that you call a router, you have a cable modem, or you have a Fios modem, and you connect to that a bunch of devices that you have inside of your house. That's a home network. It's similar, not the same, but similar to an institutional network. A home network, you might have a handful of devices. Maybe if it's a large family or what have you, maybe you have a dozen, 2 dozen devices, but usually you have a few, 3 to 10 devices is typical for an average home. Whether you realize it or not. So if you have maybe an Xbox that's connected, if you have like a Roku, one of these video streaming boxes that's connected, you have a desktop, maybe you have a tablet. So it's typical for a home to have a handful of devices that are connected in through this router. They push traffic into the router, and that makes its way onto the regional ISP and can contact all sorts of other machines on the other side. And so then you also have mobile networks. This is the phone system. And so the phone system has a network, and that's your LTE, your 3G or your 4G, and of course 5G is becoming much more pervasive, especially in 2020. And these mobile networks will provide data, right, to your cell phone, can provide data to automobiles and all sorts of stuff. In fact, as I've come to understand, if you're familiar with the Tesla products, the Tesla autopilot autonomous driving feature is really, really good because it collects a lot of data. And that data that it's collecting is a lot of sensor data. And even if you never have it driving autonomously, it's collecting data on your driving habits and using that to help train these models that do autonomous driving. So that's why Teslas are so good in autonomous driving. And they use the cell phone network to collect this data. Right, it's constantly phoning home, if you will, uploading this data into ultimately Tesla's data centers. And so this mobile network allows you to walk around, and it's the cell tower that has these big antennas, kind of like a big Wi-Fi antenna, but it's not Wi-Fi, and it allows you to communicate wireless. And that itself is also another type of network. So the cell tower is a big antenna, if you will, and it's connected to a router, which is connected to an ISP, which can push these units of data, these packets, anywhere into the network. Does that make sense? Okay, any questions? Okay, so this is the nuts and bolts view. And so in this system, we have a bunch of networks as depicted here. We have an institutional network, we have a regional ISP network, we have a home network, global ISP, and a mobile network. And you'll notice here, these networks are connected to one another, right? They're inter-networked. So when you talk about internet, it's a network comprised by connecting together smaller networks. And this is just one schematic, and it's the schematic that they use in the book to explain what the internet is. So there are a lot of devices in this network, the so-called hosts or end systems, and they're called end systems or sometimes edge devices because if you trace a path from one side of the network to another, you start at one of these devices, and let's say we go across and we end up at a cell phone. If we trace a path from one end of the network to the other end, we encounter these devices. And so for that reason, it's called the network edge, at the edge of the network, or it's sometimes called a host, like a host computer, or a so-called end system. Those are all synonyms. So we have these devices, and we have billions of them, lots and lots of these devices. I wouldn't venture to say, people estimate this thing, how many devices there are connected, but there are lots of these end systems or hosts. And these hosts are running applications. And these applications are special applications because they don't just exist in one place. Part of this application runs in the end system on this side of the network, and the other part of this application runs in this computer, maybe it's in a data center, on the other side of the network. So for example, when you hold down your iPhone button, if you have that version, and you run Siri, and you say, Siri, get me XYZ or tell me XYZ, Siri exists a little bit in your phone, but also in a data center running on the other end system in one of Apple's data centers, right? When you run Google Maps, part of that application is running in your cell phone or your tablet, and the other part is running on some host somewhere in a data center in one of Google's data centers. And so these two pieces of software are running at the same time, and they're exchanging information with one another, and they're doing it in a way to give you the illusion that it's a single application. So to you, when you run Google Maps, it's not really apparent to you that this is running partially on a data center. right? And that so-called network application is really taking an application and sort of scattering pieces of it across the network that communicate with one another to give the illusion of a single application. So we have these end systems, whether it's a server instance in a data center or it's a tablet or a smartphone in your hand, and these things are running network applications, right? Later we'll learn when we talk about application layer what these pieces are called. But for now, we'll just say network application. Okay, and so we also have these links, and these links are these physical components that allow you or facilitate the acceptance of data and the transmitting it over some distance. Now, there are different types of links. There are physical wires, like you see here in an institutional network or a home network, but there are also links that are wireless, right, like Wi-Fi. And how that wireless link works, it uses radio frequency signals, so electromagnetic, it's technically called radiation. I don't want to make it sound scary. Electromagnetic encodings of information as the quote unquote link. It's not a physical wire or physical fiber optic strand, but it's a communication established between two entities using wireless, right? Using electromagnetic energy. And so we have these links, and there are different types of links. There's fiber optic links, which is basically glass, and you can pass pulses of laser light through that glass at a very high rate of speed to give you high speed communication. Um, you also have copper wires, which is, kind of becoming less and less prevalent. And then you also have radio and satellite. Satellite is nothing more than radio in the sky, if you will, at different frequencies, higher frequencies. And so you have these communication links, and these communication links, based on the nature of the link and interference in the environment and stuff like that, can transmit data at a fast rate or maybe at a slower rate. And so what you're concerned about with these links is both the physical composition of this link, be it wired, fiber, or wireless, as well as the bandwidth, how fast it can communicate. Now, that speed of communication is called bandwidth because that translates to the amount of data per unit time that you can transmit. And so you'll notice, of course, when you maybe run something on your cell phone, maybe the video is a little bit more sluggish versus when you plug in to an Ethernet link, it's a little bit faster. And that's because wired communication is higher bandwidth than wireless communication. Okay? All right. Any questions about this? Does that make sense? So we have these end systems or hosts, and we have these links, and each link has a certain bandwidth characterization or transmission rate. And so we also have these so-called packet switches. And the packet switches look like these look like Altoids with a little X on them. Little Altoids mint candies, but hockey pucks or Altoids, whatever you want to call them. And these packet switches are two different types of devices. One's called a router, one's called a switch. And these packet switches are responsible for trafficking in these units of data or packets. And so these chunks of data or packets, these devices, the routers and switches, the packet switches, they input a chunk of data, analyze it, and depending on its analysis, will output that data along a particular link. So what you'll notice here we have a router, and that router has links from the wireless router and these four machines. And so let's say this machine inputs a packet of data into this router, it'll analyze it, and based on the information, forward it out one of its links. And so it's through that analysis, the storing, analysis, and forwarding in aggregate that gets your packet from one source endpoint on one edge of the network to another destination endpoint. So for example, you originate a message here, it gets analyzed and forwarded, analyzed and forwarded, analyzed and forwarded, analyzed and forwarded, forwarded, and it gets to your cell phone, and that's now your response from Siri, for example. Any questions about this? Does this make sense? So we have these three classes of components. We have our end systems, we have our communication links, and we have our packet switches. And together, I'll get to your question in a moment, together they give rise to communications. Okay, questions? Ah, um, to use Siri, it would start in a data center, and a data center looks like an institutional network. It's not exactly an institutional network. For example, if I were to draw something a little bit more realistic, and that's a great question. You have an institutional network, maybe that's like DSU, and then you'd have maybe a data center, and maybe this is owned by Apple, wherever it would be for this region. Maybe it's somewhere in Philly, maybe it's somewhere in Maryland, probably either Maryland or Philly, one of the two for the Mid Atlantic. And then you have the regional ISP, and then you have the global ISP, and then you'd have maybe a mobile network, right? So when you're using something like Siri, let's say you have your handset for your cell phone here. Um, it would be served by a host that's running in a data center. And a data center you can think of as a specialized institutional type of network. And the reason why I say specialized is because that data center is very highly tuned to getting flows of data to happen very quickly. And we'll talk a little bit about data center architecture. But to answer your question, institutional network refers to something kind of like a college campus where you have a number of different organizations that subdivide the way the bandwidth comes in and out of that university. And so you can imagine when if somebody goes to Netflix.com, right? Um, First, it makes its way to DSU's network, and then from DSU's network, maybe it makes its way to the admin building or to the dormitories or to the MLK Center, right? And so what an institutional network does, it takes that very high speed bandwidth link to an ISP, and then it subdivides the network into smaller pieces based on some purpose. So at DSU, I know we have the academic network, which is where the classrooms are on. We have the research network, which is what the research labs are on. You have the residential network, which is what the dormitories are on. You have the business network, which is what admin and registrar and those things are on. And so this institutional network uses routers to subdivide based on the organizational function. Okay? Does that answer your question? Okay. Any other questions? No? All right. So this is these are a bunch of internet connected devices. Now, this version of the book was published in 2017. It's now 3 years later, and it's starting to become obsolete already. But there are lots of internet connected devices. You can have sensors that are internet connected, and especially the smart home space is where there's a lot of movement happening on network connected devices. The Ring doorbell. I know Amazon, when they bought Ring, they're now experimenting with a service with a smart connected lock so that when the delivery person shows up at your house, they can unlock your door, put the thing inside, and unlock the door. I don't think I would ever want to do that, but some people like that idea. You also have internet connected things like refrigerators. You can imagine having RFID tags on your food, right? And when you take the food out the fridge, the RFID tag is scanned and it knows what your inventory is of food in the house. And when something goes below a certain level, it then generates an order, and the grocery gets sent to your house, right? And you're notified, and it bills you, right? So there's lots and lots of applications, and this is hardly representative of what's out there. Where it'll go, I'm not going to venture to guess, but there are lots and lots of internet connected devices, be they entertainment or something that has very high utility. Okay, let me check the time. So that's what the internet is. And the internet really is a network comprised of networks. So you have a bunch of interconnected networks, and that's literally what internet means. And this is achieved by connecting together these internet service providers, or ISPs. And then you also have what's called protocols. And a protocol, when I ran Wireshark, you saw some of them. A protocol is nothing more than a scheme for interacting between two communicating endpoints. And when we talk about protocol, a protocol is meaningful for certain aspects of this internet. And these protocols are defined by so-called internet standards. And these things are publicly available. There's no secret to them. And they're called RFCs, or requests for comments. And so if you wanted to implement a web browser, you can look up the RFC for a certain version of HTTP, and you could just implement it, and your web browser will work with any web server. Likewise, with a web server, if you wanted to implement your own web server, you just look up the protocol version from the RFC for that version of HTTP, and your web server would then work with any web browser that supports that version. And so the standards is what allows this interoperation. Any web browser can work with any web server because of these Internet Protocol standards. So the protocol defines the message format and the message contents and the behaviors that the endpoint should engage in when they get these packets. The standard here is the written form of what these things are. Okay? Any questions about this? Make sense? All right. So let's take a slightly different view of the internet, and this is the so-called service view. And the service view talks about all the capabilities or behaviors that these components engage in. And so this internet has a bunch of infrastructure components, and these infrastructure components are useful generally in writing some application. So for example, the web, HTTP. There are a lot of applications that are built up on top of HTTP, right? Voice over IP revolutionized phones. Now before, at least in the old days, I remember when I was a kid, if you moved to another state or another city, you had to change your phone number. With voice over IP, you could be anywhere in the world. Someone dials your phone number and it rings you in the right place, right? Things like email. Email was a huge breakthrough, and I know email is kind of blasé now, but email was a huge advancement. And there are a bunch of services, simple mail transfer protocol, that standardizes how email goes back and forth. And it's the reason why I could be running email on Linux and you can be running email on Windows. I can send you a mail, you can send me one, and we'll both get each other's message and it works fine. It's because of these internet standards. And so you have infrastructure that provides services or the ability to do things on this internet stack. And it also provides interfaces so that you can write software to use these facilities. Okay? All right. Any questions about this? Does that make sense? All right. I'm losing my voice after not talking for 3 weeks. So what is a protocol? A protocol is an interaction between two communicating entities. One initiates the communication and one responds to the communication. So an example, if I were to ask, I don't have a new watch yet, my old watch broke, I say, hey, anyone have the time, right? Do you know what time it is? So someone will look at your watch and you'll tell me it's, such a clock. Well, actually, what time is it? It's 12:57, thank you. And so that's an example of a protocol. So when you engage in a protocol, the two communicating endpoints have to be ready to communicate. And what that means for computers is that they have to answer the question, do you have the resources to engage in this communication? Yes or no? And once that answer is a yes for both the communicating endpoints, then they engage in that exchange of a message and the response. So here where it says in a human example, do you have the time, right? You have a watch. I'd say, is anyone wearing a watch? You say yes. And say, okay, do you have the time? You then look at your watch and then you tell me back the time, right? So that's an example of a protocol. Now with a network protocol, of course, you have two communicating machines. It could be a computer, it could be an embedded system, or what have you, instead of people. So a protocol defines the format, the order of the messages, the content of the messages, what message is sent, what is received among entities across a network, and the actions that are taken when you receive certain values in these messages. And that altogether is a protocol. So if you were to read the RFC for maybe HTTP, it's going to describe what the messages are, what values they can take on, and what actions the browser should take and what actions the server should take when certain values occur in these packets. Okay? Any questions? Does that make sense? Okay. So you'll see these so-called protocol diagrams all over the place. And this protocol diagram typically has 2 columns, right, or 3 columns. In this case here, we have Alice, who's on the left, and we have Bob, who's on the right, your right. And these two columns, or these entities, represent the two things that are communicating. And so the arrows, the direction of those edges, represents the direction of the communication. And when we read this protocol diagram, from top to bottom represents time. So in this particular case, we see an edge from Alice to Bob. So Alice first sends a message to Bob, and Alice's message to Bob contains the value high, and that happens first because it's first up top, going from top to bottom. So time increases going in the downward direction in these protocol diagrams. So Alice first says hello to Bob. It's a greeting message, and this greeting message is usually used to ask the question, do you have the resources to participate? So then Bob answers back, hello. Bob gives back a high response saying, yes, I have the resources available to participate. It's like my asking, do you have a watch on? Yes. Okay, can you tell me the time? So once this message is initiated by Alice and the response comes back from Bob, Alice now can proceed to engage in the acquisition of the data she needs. So she issues the message, do you have the time? So then Bob does some work, accesses his local information or resource, does some work, reads his watch or clock, and then sends back the response on Alice. So when you send a message and get back a response, that's called a round trip, right? You go there and you come back, it's a round trip. So the first round trip is establishing the resource, and the second round trip is the actual message. And when this initial request occurs from Alice, Bob does some work and then returns a response, and that response is the result of that work. So in HTTP, it's called Hypertext Transport Protocol because the work that your browser is asking the server is to retrieve this file from disk. And that file is an HTML file. And when that HTML file is sent as a response back to the browser, your browser reads the HTML file contents, and then it draws on the screen all of those commands that were in the HTML file. So that's why it's called Hypertext Transfer Protocol. Okay, so going to the machine example, you have transmission control protocol, which is what HTTP is built upon. And the first thing that happens in the first round trip, the initiator initiates what's called a TCP connection request. And what that is, it says, okay, I want to engage in reliable transport of data. Do you have the resources in order to do that? So the machine checks to see if it has the resources, and if it does, it allocates them, and then responds back, I'm ready. That's like Bob's high response on the other half of the first round trip. So now that the response has occurred, that means the server on the other endpoint has the resources and it's ready to engage that request. So then in the next round trip, that machine, your browser, issues what's called a GET request. Fetch this HTML file. Now, of course, when you first type a URL in your browser and hit enter, your browser is being kind to you and it's inserting index.html on your behalf. So the first file that's fetched when you point your browser at a URL, excuse me, the first file that's fetched is the index.html file. Sometimes if it's PHP, it'll be index.php, right? And then from there, when you click on a link, that link has another URL and another GET request is issued, okay? So this GET request for URL is sent once the server is ready as a result of that first round trip establishing the resources. Then the server does some work. The work done is to go and fetch that file from its local file system. It pulls it into memory and sends it back across the wire as a response. Your browser gets it and it draws it as your web page. Okay? All right, any questions about this? Does that make sense? Excuse me. All right. So let's take a look at a little bit more about the structure. So we have the network edge, and it consists of endpoints or end systems. And these end systems are categorized as two different things. One's called a client, and one's called a server. Now, a client, recall, in the previous diagram, I said one machine or entity initiates the contact. A client is defined as that entity running on a host that initiates the communication. If you initiate the communication, you are the client. The entity that waits receives that request and responds back. That's called the server, right? And so so-called client-server communication is the way you talk about the role of who initiates and who responds, right? And that's how you structure your network applications, as clients and servers. So at the network edge, we have two type of hosts. There are hosts running client programs, and there are hosts running server programs. Now, your browser, your web browser, is a client program. When you type in www.google.com and hit enter, it is initiating a request to a server instance running in Google's data center. When you hold down that button and Siri says, "Can I help you?" and you say, "Siri, what's the temperature?" Right? Well, that Siri software on your cell phone is a client program. It's initiating a request that is sent to a data center at Apple, and that server gets the time and sends it back to you across the wire. So we have clients and servers running on the hosts, and it's very much the case today, or more modern times, I should say, that servers are generally in data centers. A server doesn't have to be in a data center. You can run a server on your laptop and use a mobile device to connect to it. There's nothing special about a server. The reason why servers tend to be in data centers is because you need a lot of computational power for a lot of these modern applications. To do things like mapping, you need all of this geographical information, both the pictures or the satellite images, the streets, and all that stuff. That takes a lot of computational horsepower. And moreover, you have millions of people accessing it at the same time. Now, that's not going to work well if you're running that on a laptop. And so in order to get the computational horsepower you need to make these applications responsive, you need to concentrate them in one place, and that place is a data center. But from a functional standpoint, any machine that can respond to a request can act as a server. So a laptop can act as a server, your cell phone can act as a server. It's just the role in a network of that entity that responds to requests. No more, no less. Does that make sense? Any questions? Okay. So we have these servers. They're often, but not exclusively, in data centers. And then we have the access networks. It's how these end systems gain entry onto the network. Now, these access networks, institutional is one, home is another, and mobile is another. Data center is another type of access network. Now, these access networks can have different types of media or ways they access. It can be wired, like a machine plugged into a network. It can be wireless, like your laptops accessing the access point for CIS Wi-Fi. It can also be a fiber in very specialized cases, right? And so we have the access network, and then we also have what's called the network core. The network core corresponds to all of these switches that are connected to one another. And if you think about what happens, you have all these devices that are interconnected with one another. Sometimes it's called a switching fabric, right? Because these links, if you have a lot of links, it almost looks like you're weaving a sweater or something like that. So you have the switching fabric is your network core, and this is comprised of a set of interconnected routers. And some of these routers' purpose, it's called the gateway, is to connect one network to another network, one ISP to another ISP, this ISP to that mobile network. And those routers that connect you to another network are called gateways. Okay? All right. Any questions? No? All right. So let's take a look at some of these access networks, and we'll spend the next 5 or so minutes doing that. So we have residential access networks, we have institutional access networks, and we have mobile access networks. And each one has a certain bandwidth characteristic associated with it. And so certainly residential access primarily is done through things like Verizon Fios, these home network packages. Absolutely, you could call up a commercial ISP, like a global ISP, and say, I want an access network. And they'll give it to you, but they're not going to give you, 25 megabit bandwidth. They want to give you 100 or a gigabit or multiple gigabit. And you're going to have to pay a lot of money for that. And so some of these global ISPs, they traffic in large quantities of data, right? But you could absolutely call up Sprint, Verizon, all those, Cogent, and ask them for a high-speed connection. So there's nothing special about that. It's just enterprises typically need these higher bandwidth connections because they have a lot of data aggregated together and therefore need that high bandwidth, right? But there's nothing special about those particular ISPs. Okay? So we have different bandwidths associated with the different access networks, right? So if you are dealing with Verizon Fios and a residential ISP, of course, you might need 25 megabit, maybe 100 megabit. Right now in Dover, there's gigabit for residential. Maybe you have a need for that. You can absolutely do that. And so typically for these different access networks, there are various bandwidths associated with them, and also the characteristic associated with them is whether or not that bandwidth is unique to you, meaning only used by you, or if it's shared with others. And I'll explain a little bit, hopefully, what that means. Does anyone have DSL, digital subscriber line? It's kind of old by today's standards, but in the earlier days, and even still now, depending on where you live and the population density, they started out giving internet service using the phone lines, the regular hand phone, landline. And in order to do that, they took the data signal and they changed its frequency so that it wouldn't interfere with the voice signal. And so that became what's called digital subscriber line. And how that DSL worked was they had the special DSL modem and they had a splitter. And what it would do, this DSL modem stands for modulator demodulator. And to change something's frequency is to modulate it, right? And so what it would do, it would take the data and it would shift its frequency so that it wouldn't interfere with the voice for the telephone. And so it would join together those two signals into a DSLAM, which is a digital subscriber line access modem. And that DSLAM would then take that data, split it apart, send the data through the computer network, and send the voice through the telephone network. And so that's how internet, high-speed internet, when I remember it was 128 kilobit, and I was like, woohoo, you know. But you didn't have a lot of video streaming back then. Back then, it was just static web pages, no animated GIFs or anything like that. It was pretty basic by today's standards, but I was excited. I was the first one in my building that had DSL, right? Company paid for it. But anyways, so that is DSL. And with DSL, voice and data are transmitted together and then split apart once it gets to what's called the central office, which is a facility that has equipment from the phone company. So DSL got faster and faster and faster, but it could only do about 2.5 megabit per second, which is pretty slow by today's standards. But we have to remember, this copper wire was originally intended for voice, right? And voice does not take a lot of data. And so they tried to kind of stuff data into this copper wire that wasn't originally intended for data, right? And so they kind of pushed the limits on bandwidth, and you can no longer do it anymore. So this is what a phone wire looks like. It's copper, it's a conductor, and you have 8 of these conductors. One is positive, one is negative voltage, the ground, and you had 4 of them, and one was used to provide power for the phone, was used to provide voice, and they had the other 2, which I can never remember what they did. But regular landline look like this. It looks a lot like a network, but it's not a network, it's a telephone wire, right? And that was what the physical medium looked like, and they used this to do DSL. Now, cable TV came out, and if you remember cable TV, well, maybe you don't. I remember when cable TV came out. My parents would never get cable TV, but anyways, that's another story I'm still salty about. But anyways, cable TV, you were originally purposed with sending television. That's voice and video, audio and video. So video is much more higher bandwidth, and cable, the coaxial cable as it's called, can accommodate much more data. So somebody said, you know what? Maybe we should send computer data over this cable for cable modem TV. And so what they did, again, is they divided the bandwidth for this coaxial cable into so-called channels or frequency bands. So I have 2 more minutes. And they sent TV and voice down some of these channels and computer data down others. And so you have a cable splitter and a bunch of homes here. They all share the bandwidth because originally they all shared the same video. So that's why you have shared bandwidth for a cable modem, whereas Verizon Fios, it's dedicated bandwidth. And so each channel is devoted for video, but you also have a data signal, which is used to send the computer stuff. And this is what coaxial cable looks like. It's called coaxial because you have on one axis right? In the center, that's one conductor, and along the outside, another axis, you have another conductor, and they're separated by an insulator, right? So that's what coax looks like, and you see it as this connector here that you kind of put it in and screw on, and if the pin bends, like, ah, crap, now I have to call the cable modem company and get them to get me another one. We can get them at Best Buy, but it's overpriced. But anyways, so this is what your coax looks like, and how this connects is called hybrid fiber coax, and it connects into what's called a cable head end, which is this green box in your neighborhood. You ever drive down the street or drive in the neighborhood, you see these mysterious green boxes. That is where the fiber optic high-speed strand ends and the coaxial cable begins, and the coaxial cable actually goes to the house. So we'll end with that, and we'll pick back up with that. And this is what a cable head end looks like, those mysterious green boxes. You don't want to mess with them.